So we're going to be continuing to talk about KSP. In this video, I'm going to focus on what are things that affect the solubility, how much it dissolves. Something Q again, and then I'm going to do a problem to figure out if a precipitate will form or not. So these are not in your notes in the note packet, so you need to copy them down. So there are a couple different factors that could affect how well something dissolves. So temperature, concentration, pressure, pH, solvent change, and common ion. So as we've talked before, if I increase the temperature or decrease the temperature, I will get more or less of solids to dissolve. Generally, if I increase the temperature, I will get more solids to dissolve. Again, there are some exceptions to that rule, but that's going to be the general rule. If I change the concentration, of course, I could get more to be dissolved. It kind of has to do with common ion effect, so I'll leave that till later. Pressure only applies to gases only. And as we talked about a while back, if I increase the pressure above that liquid, I'm going to get more gas to dissolve. So just think of carbonated sodas. They have to put it under such strong pressure in order to get the CO2 to dissolve. pH, that's why KSP is usually taught around acid-base chemistry. So OH or H plus, if you have any of those that could affect the solubility, so they could change the pH and that could draw out either one of those ions. Solvent change, this is going to be polar versus nonpolar. So if you change the solvent, you might get more to dissolve or less to dissolve depending upon the polarity. And finally, common ion effect is what I showed you in the previous video. So if I throw in a chloride into a solution that has a chloride in the ion, in the salt, I would see a different solubility because of that. So in line with that, okay, we are going to be looking at whether or not we have a precipitate that can form. So we're going to be talking about Q again. And we've talked about Q before. It is just a moment in time. So we could kind of see if I add a certain amount of both of these ions in solution, will I make this precipitate? So I'm using calcium fluoride as my example here. So I have calcium ions and 2 fluoride ions. So I have my KSP expression here. And this is exactly the same expression as a Q. Okay, so just like Q is the same as K, it's just a moment in time, same idea here. So just know that KSP is going to be what we call your threshold or what we call your minimum. So if you have a minimum concentration of calcium and fluoride and you multiply them together and square the fluoride, if that Q is bigger than the KSP, you will see a precipitate form. So just like before, we're comparing Q to a K. This is just a KSP. So if my Q, when I multiply the quotient of numbers, and I'm about to show you an example of this, I will get a precipitate to form. If it is less than, that means I don't have enough of those ions in order to make the precipitate. So then a precipitate will not form. If it's exactly equal, precipitate will form. Will you actually see it? Again, that's a whole other discussion. But in terms of the quantity or the calculation you'd be asked to do, you would say a precipitate would still form. Okay, but would you see it? I don't think so. Okay, so let me try this problem with you so you can kind of see how this falls in line with what we've been talking about. So we are asked to see, I'm just going to bring the camera up a little bit here. Okay, we are asked to see whether or not a precipitate will form if I have equal volumes of lead 2 nitrate and sodium chloride. Okay, so the the ionic solid that we are going to make is going to be, of course, lead chloride. And we are trying to see, do I have enough lead ions in this solution mixture and chlorides in order to make this solid? Okay. Now, please note they are saying equal volumes of both of these, but I don't have volumes. Okay. So since I have equal volumes, I could make up numbers, and I'll show you why it doesn't really matter. So let's say I had 50 mils of this and 50 mils of that. Okay. in the solution. So I have a beaker over here, and I'm going to say, okay, when I dump that lead in there and the chloride, when will it start to fall to the bottom and make a precipitate? Okay, so that's the question at hand. So I have to use my KSP expression and see whether or not I have enough in there. So I'm going to change this to a Q because it is exactly the same thing. So I'm going to multiply the concentration of the lead and multiply the concentration of the chloride and see if I compare it to the KSP for my lead to chloride, will my Q be big enough? Okay, so trick to this is if I have if I have 50 mils of this and 50 mils of that, essentially what is happening to my concentration is it's going down by a half. Now, if you don't like what I do here, do the math yourself. Take the milliliters and multiply this, get the moles, and then divide it by 100 milliliters. You will find that the concentration is down by a half. So that is why my concentration of lead here is 0.02 molar. Same thing goes for the sodium chloride. Okay, so 0.002, I have it in equal volume, so the concentration is going to be half of that. Now, this is always the tricky part. You're not multiplying this by 2. Okay, this is all the chloride that is in there. Okay, just like this is all of the lead that is in there. So I'm just going to square that value. Okay, so then I'm going to find my Q. So my Q happens to be, when I multiply this out, take the square, I get about 2.4 times 10 to the negative 8th. So then I have to go and find a KSP. And again, I would give this to you in the problem, or the AP would give it to you. We already use it in another part of our notes. So 2 times 10 to the negative 5th is the KSP value for lead 2 chloride. So obviously my KSP is greater than my Q. Okay, it's 10 to the negative 5th versus 10 to the negative 8th. So therefore I would say no precipitate forms. So you're always comparing back to the KSP for this.